Our research is about heuristic algorithm for topology optimization by Rohaya and Nana Rahmana Syambas. The first section is introduction. As you know, today the ring topology has become a standard in network topology design, especially on optical networks. How to find the minimum cost to connect all the nodes to create a ring topology network is the challenge. It is important to determine the shortest route in designing the ring topology to reduce development costs. This problem, known as traveling salesman problem or TSP. TSP is finding the best route for a salesman who travels from a home location through several cities and returns to the home location. In a such way, the total distance traveled is minimum and each city is visited exactly once. The problem statement. Using this research, we want to design a ring topology and try to find the minimum cost using a new heuristic algorithm. Then compare the capabilities of the proposed algorithm with existing algorithm for cost accuracy and computation time. The next sections related works. As we know that the traveling salesman problem is typical of a large class of hard optimization problem that motivates scientists to develop various methods for solving this problem. There are several popular algorithms for solving TSP, like brute force and colony algorithm, greedy randomized adaptive search procedure, hybrid greedy brute force, and Bambang algorithm. We will discuss this algorithm one by one in the next slides. The first algorithm is brute force. Brute force is a conventional method that tries all possible node combinations. This algorithm calculates every single possible combination and compares its value. So it takes a very long execution time but gives absolute minimum value for TSP. This algorithm is the easiest and most expensive solution for TSP. It creates n minus 1 divided by 2 factorial possible nodes combination. N is the number of nodes. The complexity of this algorithm is n factorial. The next algorithm is n-colony algorithm. The n algorithm is a heuristic algorithm inspired by n-colony behavior in finding the best path from a food source to the nest in the nature. The advantages of n-colony algorithm are reliable to find good solution and easy to combine with other methods. But this n-colony algorithm has the limitation of easily being trapped into local optimum and long execution time to find the optimal results. The next algorithm is hybrid greedy brute force. We call it SASA. This algorithm combines greedy and brute force algorithm. This algorithm claims provides fast computation time and gives 6.69% better solution from n-colony algorithm for 33 nodes through 50 nodes. And the last algorithm is Bambang algorithm. This algorithm creates a ring topology by making a tree of two lower minimum costs and tries starting nodes for all nodes 1 to n. So it makes too many iterations. This algorithm creates good accuracy better than an n-colony algorithm, but needs too long computation time. The next section, proposed algorithm. This proposed algorithm can be explained in the following steps. 1. Find nodes with minimum cost at the start node as the start nodes. The second node is pair of the start node that create a link with minimum cost. For the next node, third nodes, and so on, choose to lower minimum cost. Then the last node is the same as the first node. List all possible combination nodes to create a ring topology. Then calculate total cost for each ring topology. To make this algorithm still running for the number of nodes 50 and bigger, the ring combination must be limited into only 200 combinations for every multiple 7 of nodes connected and remove the others. And then try step 2 to step 7 for other start nodes. Then compare the total cost and get the minimum one for the best ring topology. For example, use this cost matrix and want to find the best route, the best route from this cost matrix. The first step, define the minimum cost step and find the start node is start nodes are 0, 5, 4, and 6. The start nodes have the minimum cost. And for closing to connected nodes are 0 to 1, 1 to 0, 4 to 6, and 6 to 4, which have the minimum cost. This is the possible node combinations for start node 0, and we need to list node combination for other start nodes 1, 4, and 6. In this case, we find the best route is 0, 1, 3, 2, 5, 6, 4, and back to 0, with the minimum value is 115. The last section is simulation and results. On this experiment, all algorithm running on Python 2.7 and use this computer specification. This computer specification will create the reference results of simulation. This is the results of these experiments. The first one is proposed algorithm versus brute force algorithm. This table shows comparison of the proposed algorithm and brute force algorithm. The brute force algorithm tries all combination to get an absolute minimum bad value. From this table, we find that minimum cost simulation results of the proposed algorithm compared with brute force. We can see that minimum value generated by proposed algorithm and brute force algorithm are almost the same. An error occurred at the trial 9 and the trial 14. The average of minimum value error is 0.202%. From the next figure, can be concluded that the proposed algorithm reduces computation time significantly compared to brute force. This algorithm needs only one seconds to find minimum value of 10 nodes, while brute force algorithms spend 1299 seconds. The proposed algorithm versus uncolony algorithm. The first figure indicates that the proposed algorithm and uncolony algorithm give the similar performance in minimum value. The proposed algorithm generates minimum value with an average of 0.745% better than n-colony algorithm. And the next graph shows the comparison of proposed algorithm and n-colony algorithm in computation time, with proposed algorithm running faster than n-colony algorithm. Next, the proposed algorithm versus Sasa and Bambang algorithm. The first graphs from this graph, it can be seen that minimum value generated by this proposed algorithm still higher than Bambang. This proposed algorithm gives an average 2.93% less than Bambang, and this value is better than Sasa with an average difference 15.16%. The next graph describes computation time of the proposed algorithm and Bambang algorithm. You can see that this proposed algorithm saves computation time significantly than Bambang. Conclusion. From this experiment, we can conclude that the proposed algorithm achieves better solution to get the minimum value. There are 0.754% better than an colony algorithm, and then 15.16% better than Sasa. But this minimum value still gives 0.102% error to obtain minimum cost on 4 nodes through 60 nodes compared to brute force, and gives 2.93% average minimum value error compared to Bambang. Computation time, this algorithm running faster than n-colony algorithm and saves computation time significantly than Bambang algorithm. Thank you.